Welcome to Level Programming Interview Crashcasts, your go-to podcast for mastering technical interviews. I'm your host, Sheila, and today we're diving into a classic question that often comes up in senior backend engineer interviews. Joining us is Victor, an experienced software engineer who'll help us tackle this topic. Victor, welcome to the show.
Thanks, Sheila. It's great to be here.
Let's jump right in. Victor, here's the question. Can you explain the difference between stack and heap memory allocation?
Certainly, Sheila. At a high level, both stack and heap are regions of memory used for different purposes during program execution. The stack is used for static memory allocation, while the heap is used for dynamic memory allocation.
That's a good start, Victor. Can you break that down a bit more for our listeners? What exactly do we mean by static and dynamic allocation?
Of course. The stack is typically used for storing local variables, function parameters, and return addresses. It's called static because the size of these allocations is known when the program is compiled. The heap, on the other hand, is used for allocating memory while the program is running, when the size of the data isn't known in advance.
I see. So, what are some key differences between stack and heap allocation?
There are several important differences. First, stack allocation is generally much faster than heap allocation. This is because stack memory is managed directly by the computer's processor, and allocation is as simple as moving a pointer. Heap allocation involves more complex memory management algorithms. Second, the stack has a fixed size, usually determined when the program starts, while the heap can grow as needed, up to the limits of available memory, of course. Lastly, stack memory is automatically managed by the program, while heap memory must be manually managed in languages without garbage collection, like C or C++.
That's quite comprehensive, Victor. Let's dive a bit deeper into memory management. How does allocation and delocation work for each?
Great question. For the stack, memory is allocated and deallocated automatically as functions are called and return. It follows a last-in, first-out order, or LIFO for short. This means the last item added is the first one removed, kind of like a stack of plates. When a function is called, a new stack frame is created, and when it returns, that frame is popped off the stack. For the heap, memory is allocated using specific functions in your code. This memory sticks around until it's explicitly freed, or, in languages with garbage collection like Java or Python, until the system determines it's no longer needed.
Excellent explanation. Now, can you give us some examples of when you'd use stack versus heap allocation?
Certainly. You'd typically use stack allocation for small, short-lived objects with a known size at compile time. This includes local variables, function parameters, and small arrays. Heap allocation is better for larger objects, objects with a size determined at runtime, or objects that need to persist beyond the scope of the function that created them. This includes dynamically sized data structures like linked lists or trees, large arrays, and objects that are shared between different parts of the program.
That makes sense. Let's talk about performance implications. How do these different allocation methods affect program performance?
Stack allocation is generally much faster and more efficient. It's a simple operation of moving the stack pointer, and deallocation is automatic. This makes it ideal for high-performance code. Heap allocation is slower because it involves searching for a suitable block of free memory, which can take time. It also can lead to fragmentation over time, where free memory is split into small, non-contiguous blocks. However, the heap allows for more flexible memory use. You can allocate large blocks of memory that wouldn't fit on the stack, and you can keep data alive for as long as needed.
Interesting. Now, let's consider some edge cases. What happens if we run out of stack or heap memory?
Good question. If we exceed the stack size, we get what's called a stack overflow error. This can happen if we have very deep function calls, like in recursive programs, or if we allocate very large arrays on the stack. For the heap, if we run out of memory, our program will typically receive an out-of-memory error. This might crash the program if not handled properly. It's worth noting that in some systems, particularly those with virtual memory, the heap can grow to use almost all available system memory, while the stack size is often more limited.
Excellent point about virtual memory, Victor. Now, as we wrap up, what are some common pitfalls or best practices related to stack and heap allocation that our listeners should be aware of?
One common pitfall is returning pointers to stack allocated variables from functions. Since the stack frame is destroyed when the function returns, this leads to dangling pointers and unpredictable behavior. For heap allocation, the most common issue is memory leaks, where allocated memory is not properly freed. This can happen if you lose all references to heap allocated memory without freeing it. As for best practices, it's generally good to prefer stack allocation when possible, as it's faster and automatically managed. When using heap allocation, make sure to properly free memory when it's no longer needed. In C++, you can use smart pointers to help manage heap memory, and in general, try to design your program to have clear ownership rules for dynamically allocated objects.
Thank you, Victor. That was an excellent overview of stack versus heap memory allocation. To our listeners, remember that understanding these concepts is crucial for writing efficient and correct low-level code. When preparing for interviews, make sure you can explain not just the basic differences, but also the implications for performance and program design. Some key takeaways. Understand the speed difference between stack and heap allocation. Know when to use each. Be aware of the memory management implications, and always consider the lifetime of your objects when deciding where to allocate them. That's all for this episode of Low-Level Programming Interview Crashcasts. Thanks for listening, and good luck with your interviews.